Okay, so hello and welcome to PyData Global 2021. My name is Rosa and I'm glad to be here, the host of this workshop. The workshop that we have right now is about behind the black box and how to understand any machine learning model using Shap library. And our speaker is Jonathan Bechtel. Did I pronounce it well? Sorry.
Very well. Yeah, it's a German last name. So you
exactly.
Actually,
I know.
Yeah,
German,
yeah.
so
No, actually,
like
your guttural pronunciation was actually much better than even I pronounce it. I think. Yeah, that's perfect.
And is the lead data science instructor for General Assembly, which is a global technology education company. He has delivered over 1,000 workshops and corporate trainings to students on the subjects of data science, programming, and machine learning. And his corporate trainings have helped companies in the private equity, consulting, accounting, and hedge fund industries to incorporate analytical tool chains and realize the power of data-driven decisions making and business processes. So I think that was my part here. I'm going to stop sharing.
Thank you. All right. So awesome, everyone, for being here. I see this beautiful, panorama of different people in attendance here from all across the world. So it's definitely flattering to know that we might have someone from almost every single time zone, right? Kind of in this workshop here, to learn more about data science and model interpretability. So it's definitely a privilege to have you all in attendance. So thank you very, very, very much for being here. We'll cover a little bit of errata, and then we'll just go ahead and jump in. All right, so let's kind of go ahead here. Let's get the party started. All right, I'll start my presentation. All right, and we'll go from there. All right, so the workshop here that you're attending, it's called Behind the Black Box, How to Understand Any ML Model with Shap. All right. So I'm going to be your teacher here for the next 2 hours. Very excited to do it. Definitely think we're going to have an awesome time. We're going to cover a lot of interesting material. And again, having so many people from around the world, I think is really inspiring. So thank you everyone for your attendance. A little bit of background about me. In terms of my, my official credential in life, I have an MS in analytics from Georgia Tech. I work for the last 4 years as a data science lead here at General Assembly. It is an education and consulting company in the tech and programming space. And so I work mostly in their data science department, which covers, some aspects of Python programming, machine learning, and then just general data science. And so things are taught both to adult students as well as, corporations on site. And then I also work individually with companies, mostly in the New York area, because that's where I'm domiciled, but also, a few that are scattered, throughout the country as well. And so the work there is also pretty similar, kind of helping companies set up their data systems, throughout their organizations, and then just build out various types of analytical solutions and platforms, on top of whatever it is they're looking to go ahead and then solve for the company. All right, so I've been doing this for about the last 5 or 6 years. I've been working with data in general, for about the last 10. If you want my official watering hole on the internet to kind of understand more about me professionally, my website, www.jonathanbeck.tel. Okay, feel free to wander over there if you just want to get a closer look at what I do. Obviously, if you search for me, you can find my LinkedIn profile and then my General Assembly teacher page, things like that. It's not too hard. So if you're curious, you're only a Google search away from getting into more detail on what's listed on the slide. But that's kind of the postcard version of me. If it were a normal workshop, I would expect there to be maybe 10 or 12 different people, and I would have us introduce ourselves. Being that there were 100 plus, I don't think that's going to be feasible. So we're just going to go ahead and just kind of talk about the agenda and then just dive right in. All right, so the idea is, we're going to talk about a software library called Shap, okay? And the big idea here is the real theme behind this morning's workshop, or morning for me, afternoon for you all, is we're going to talk about the general idea of model interpretability, okay? and kind of how for a long time there's been a fundamental trade-off between models that are very, very accurate and then models that can be easily explained. All right, there's a natural tension between these two paradigms. And Shap, I think more so than any other solution, has really brought a lot of closure to this trade-off. And in the last 2 or 3 years, it's very quickly established itself as, I think, probably the best way to really understand and explain nonlinear black box models. I have definitely found a lot of use for it in my professional life, because a lot of times, you know, if you're trying to actually build out an analytical solution for a company, getting buy-in from various people who don't maybe understand the models themselves is typically very important. This is usually a pretty important bridge for that. So what we're going to do then, okay, we're going to talk first about some of the theoretical foundations of Shapley values, which is what the library is built off of. So we'll kind of go ahead and then build some from scratch. Later on then, we'll actually take a look at the software itself, okay? That's what Shap is, okay? Is pretty much an improvement on the idea of a Shapley sampling value. And then along the way, you know, we'll go ahead, we will get some practice, you know, we'll go through some exercises and some of the links to the workbooks. There are some exercises that we'll have you do so that we can kind of get some hands-on practice. You know, we'll kind of go over some real-world implementations. And, you know, to specific answers, you can go ahead, questions you can answer, sorry, with the software itself. And then we'll go ahead and then wrap everything up after that. Okay, so that's what we're going to be going ahead and doing. And this will be very, very fun. And let's just jump right in, okay? Right, so definitely I think if you look at a lot of the workshops here at PyData, you know, there are usually kind of several themes that are recurrent throughout the whole, you know, the whole event. Definitely one here that you see now is interpretable ML, right, in various ways, how to understand models, you know, to make them more easily explained, you know, maybe to prevent bias, you know, to better understand where they might work well or not work well, okay? So this has definitely become a very important theme as machine learning has become more prevalent, right? I don't think this is going to go away. All right, and then like I mentioned here previously, all right, when it comes to model interpretation, there kind of is this fundamental tension, okay? You could say on one hand, we have older fashioned models, all right? These are usually grounded in traditional statistics. So things like, you know, linear regression is probably the primary example, which is still probably the most commonly used statistical technique used throughout industry in various ways, okay? Simpler models typically are not as powerful for finding generalizable patterns inside your data, okay? They're just not. Their learning technique tends to be a bit on the shallow side. But one of their big benefits, though, is that being able to interpret these models is typically fairly straightforward. Okay, so once you go ahead and you fit them, you have pretty clear explanations in terms of what's happening. All right, on the other end of the spectrum, you have models that are more complicated, okay? Their pattern recognition capabilities are definitely stronger and greater, okay? However, though, it's very, very difficult to be able to map inputs to outputs. Okay, so therefore, right, you might have something that's highly accurate, but it can be very, very difficult to really understand exactly what's causing their results. All right, and so people typically are going to be slow to trust, you know, things where they don't actually understand how and why they work. Okay, likewise, you know, if these sorts of models have certain blind spots or biases or areas where they won't perform well, it's perhaps a bit more difficult to understand that if you can't actually understand what's going on the inside. All right, so if you want a few examples of each, all right, so things like linear and logistic regression, naive Bayes and exponential smoothing are probably good examples of simpler models. They're still widely used, and lots of times they are very, very helpful in a lot of circumstances. I'm not saying they're invalid or it'd always be a bad idea to use them, but rather just their learning technique is a bit on the shallow side. Okay, complicated models, which are becoming all the rage these days, definitely, you know, probably they're covered in more detail at something like PyData, right? So things like neural networks and then various types of tree-based models, right? So random forests or gradient boosting machines. Okay, these things do tend to give you better results. Okay, they have more elaborate pattern matching criteria, but of course, it's a little bit difficult to kind of understand exactly how they impact results. Okay. So it's generally been the case, right? As machine learning has become more and more prevalent, as compute power, right, has become larger and larger and larger, our data has gotten bigger. Okay, the distance between machine learning models and more traditional models has gotten wider and wider and wider. Okay, so therefore, the performance benefit that they give you, right, becomes more salient, it's more relevant. But at the same time, it also means the need to actually understand them has actually gotten much larger. Okay, so kind of a good example here when it comes to maybe just the dominance, right, of complicated ML models compared to more regular means. I'm going to go ahead and post a link here on the Zoom if you want to look at it. These sorts of slides, these sorts of studies tend to come up, I think, fairly often, but this is probably one of the most comprehensive. All right, the title of the paper was an empirical comparison of supervised learning algorithms using different performance metrics. This was very, very widely cited, has a little over 2,000 citations. So what it did, looked at 8 different data sets, went ahead and used 9 different metrics. The total number of models that are used, I believe, was actually 2,000. But in terms of the ones that they actually ranked, it was 30, okay? And this kind of ranged anywhere from simple, linear regression, to a deep neural network, okay? And then the overall results, okay, were pretty lopsided. The top 5 performing models across the 9 metrics, all right, were all complicated, meaning they're either deep neural networks or tree-based ensembles, okay? Boosted decision trees did particularly well. If you look, they took the top 2 spots, all right? And then also, if you look at any of the individual categories, same thing, the highest performing model in every single unique scoring metric was also a complicated model, okay? I think anyone who's worked a lot with ML is not really surprised by this, okay? The reason why ML is a thing, right, is because their pattern finding capabilities really are pretty robust, all right? So I don't think this was an unusual example. And I think lots of instances in real life, these results have played out in a similar way, okay? Generally speaking, if you really want to understand patterns that are within your data, bigger, more performant black box machine learning models are typically just going to give you better results to work with. But of course, the reason why they give you good results is also why it's difficult maybe to kind of understand what they're doing, okay? Because they don't offer exact analytical solutions, okay? They're approximate solutions, all right? And so it turns out in practice, approximate solutions are usually going to outperform analytical ones, okay? Simply just due to the nature of the data that they're studying. All right, but still, I've noticed in a lot of circumstances, okay, more complicated models oftentimes are not always used as often as they ought to be. And the big reason why is because people like to understand with a certain level of precision, how they might actually be able to expect the results to be, okay? So a lot of times, a model that's not particularly good or powerful, but is easily explained, sometimes will get more airplay than it deserves, all right? So currently, I work with some companies who work in finance. This might come as a surprise to people, but in finance, linear regression is actually still used pretty extensively, okay? Not without good reason, all right? Because a lot of underlying financial theory is actually based off of linear models. If anyone's familiar with the capital asset pricing model, or 3-factor investing models, that came from like the Chicago School of Investment Theory, things like that. All of this is kind of based off of doing various forms of linear regression. But in any event, one of the big benefits, right, of linear regression is that you can kind of quantify your results very, very carefully. And so there are a lot of careful experimental designs, for different types of setups and things along those lines. And so it gives practitioners an easy way to communicate results to people who might have a stake in an investment that don't really understand the quantitative methods themselves, okay? So for me, I think a slide here or a comic that actually captures the sentiment pretty well, all right, is you might have something like this, right, where sometimes you're using a model which is not particularly powerful for capturing the patterns inside your data, but it does kind of allow you to talk about your results with a certain level of precision, even if those results themselves aren't particularly good, okay? So things like confidence intervals, okay, estimates of uncertainty, okay, statistical significance, things like that. All these things, I think, tend to be very comforting to people who are at the helm of like a decision, and maybe they can't actually understand at a practitioner's level what's actually going on behind the model artifacts, okay? Right, so in this case, right, we sort of mentioned we have a forecast, to say, we predict there's going to be a little over $4 million in sales, okay? And of course, we can actually think this is accurate, but we can kind of sort of say like our results, can kind of sort of have like this particular confidence interval to them, level of significance, things along those lines. And so there's a reporting framework around model results, which often is very, very important as much as sort of like the predictions themselves. Okay. So in any event, this framework tends to be pretty powerful. There are a lot of industries, like finance, like insurance, maybe certain types of, government agencies, where the models that they use are actually governed by how interpretable they are, okay? And so literally, regardless of what kind of results that they're going to get, if you're doing something like credit scoring, okay, where maybe you're approving or disapproving loan applicants, you have to be able to explain why you're getting your results to people, okay? And if you can't do that, it doesn't really matter how accurate the results are, okay? So for this reason, there are quite a few industries who stick to things that are very, very well understood, even though there are probably some other solutions which might be more beneficial in terms of improving their bottom line. Okay, so in any event, interpretability in lots of different types of corporate contexts definitely kind of applies some elbow grease to being able to use various types of methods, okay? It legitimizes lots of different techniques. Okay. So that kind of brings us to where we're at right now, okay? So you have complicated, nonlinear, I don't like to use the term black box, but it's a common term, okay? So if we're using the vernacular of the day, right? So this idea of being able to use highly powered models, but then also have some capacity to understand their inputs, I think is just really, really important. Obviously, if you're doing Kaggle competitions, or if you're at some kind of AI startup or things like that, you can just kind of use your biggest, baddest neural network or whatever and call it a day. But for lots of other companies, right, that are trying to kind of incorporate ML into the regular business practices, that's not necessarily going to fly right away. Okay. So currently, there are some solutions that are often put in place, for understanding nonlinear models. The most important one is feature importance. So this is, if you fit a random forest, or a gradient boosted machine, I believe you can do this with a neural network as well. The idea is what you can do then, all right, you can randomly shuffle the values in certain columns and then look to see how much your model performance is affected by, and just kind of sort of, sum up and average the absolute value of the effect. Okay, and so you typically, if you're done something like scikit-learn, when you're done fitting your model, you have something kind of like this, where each individual column inside your data set, how much of the model performance was attributed to each individual column. There are some other things you can do as well, like partial dependence, if anyone's familiar with that, okay? But this is typically kind of like the first step that people often take when it comes to understanding model results. This is not a bad thing, right? So what we're looking at over here, right, are feature importances for the Boston housing data set. If anyone's not familiar with it, it's probably the most commonly used data set, for kind of studying regression problems. It's extremely common. It's built into scikit-learn, lots of other libraries. Okay, and so we're seeing over here, right, columns, that represent different aspects of information about a house. And so if you regress, all these things against housing prices, it turns out number of rooms, and then something called LSTAT, which is percentage of the population that's low socioeconomic status, account for 80% of the results, okay? And then all these things kind of add up to 100% at the very end, all right? And so this kind of tells you, right, something like room has the most importance, followed by LSTAT and, distance, things like that. This is okay. It's not too bad. It's kind of like the standard output, for these sorts of things, if you're dealing with a nonlinear model. There's a lot of information there this does not tell you, okay? It tells you the absolute level of the importance, but it doesn't actually give you the sign, okay? If overall, values in this column tend to push it upward or downward, okay? It doesn't really tell you about individual values, okay, within your data set, which is often very important, okay? So this is a global interpretation of your data set, but oftentimes you need local interpretations, okay? So for a particular circumstance, right, how much is one particular value, going to go ahead and impact the results one way or the other? Okay, this tells you nothing about that. Okay, and so collectively, all right, these three shortcomings actually make it kind of a tough sell to use a model like this, when this is kind of all the output that you can get from it. Now, of course, there's been a lot of improvement on this in the last couple of years. Shap is kind of one of the big step forwards with that, but there's some other libraries as well. So it's becoming less and less true that feature importance is all that you have at your disposal. But again, it's kind of like the standard ground zero, kind of like step you might take for model interpretation. It's kind of weak sauce, okay? There are a lot of things it's not going to be able to do. All right, and so really being able to overcome these shortcomings is by things like Shap, and then other advancements in interpretable ML have kind of gained so much traction recently. All right, so with that said, okay, when it comes to understanding nonlinear models, okay, something that's a little strange about it, okay, something that's fundamentally different about something like a gradient boosted model or a neural network and something like linear regression, okay? If you have a simple model, okay, when you're done fitting it, the model gives you both the prediction and the explanation itself wrapped up into one, okay? Like you don't actually have to go beyond the model itself, right, to get that information. So once you fit it, then you're done. All right, what's a little bit tricky about interpretable ML for nonlinear models, okay, is you actually need two separate models, okay? The one that you use to fit your data on, okay, to make your predictions or whatever, okay? And then what you need then is a separate model to explain the model that you fit, okay? So it's kind of the derivative model or the secondary model, whatever you want to go ahead and call it, okay? So once you're done with something like a random forest or a neural network, okay, then you need to go ahead and apply an additional technique to make sure you can understand how different values are contributing to the output, okay? It's a little bit difficult maybe to wrap your head around, right? So the model for the model, right, to make sure you understand what's happening with it. But if you actually want explainable ML, this is basically what you have to do, okay? So when it comes, okay, to what kind of properties, okay, an explainer model should have, there are basically three separate criteria, okay, that you need to be able to meet, all right? All right, the first criteria is called local accuracy, all right? Local accuracy is basically kind of built around this idea that if you actually add up all of the contributions, right, from your individual features, they should actually basically equal your final model's prediction, right? So meaning if you kind of take your final prediction and then break it down into all its individual components, and then you add them back up, there should be a certain parity, all right, between the two, okay? Missingness basically kind of states that if you have an unimportant feature, removing it from your model shouldn't impact the results, okay? And then consistency, all right, basically states that if you have a particular value in a column and you hold everything else constant, increasing it or decreasing it, you should be able to see the influence of that particular value or feature kind of change in accordance with it, okay? If you want maybe something that's a bit more tactile and concrete, okay, in terms of what these things mean, I have some slides over here. If you would like, though, okay, you can go ahead and then go to the URL. So what this is an ML application that was fit on a data set of about 4.5 million different police stops. And it's designed to sort of understand what contributes to a particular policing outcome And so you can kind of like put in different values over here. The main idea though here, this is kind of a working example here of kind of like what like, a model interpreter should have. Okay, and if you just kind of go down and then hit run analysis here at the very end, you'll be brought to the screen, okay, which is kind of the chance of arrest for a person in these particular circumstances, okay. But in any event, if you just kind of want like a screen that's going to match the slides here, okay, you can go ahead, if you go down here and hit run analysis, you'll get the result, and that will have basically give you a screen that's matching what I have on my own slides. All right, so the basic idea here, all right, local accuracy, okay, is basically built around the idea, all right, if you add up the final overall contributions of each individual column, okay, it should actually give you, okay, the final model prediction that you're working with. So in this case, all right, in this case, we're starting with the baseline value of 35% in terms of an expected outcome. All right. If you actually add up, okay, the contributions of each individual feature value inside the model itself, right? 10, 7, -6, -5, 1, 5, 9 up here. Okay, it should add up to this right over here. Okay. So this idea of completeness. Okay. So the final model prediction can be cleanly broken down into its individual components. And then if you add up the individual components, you end up with your model's final prediction. Okay, that's what local accuracy is. Okay, missingness, okay, right, same thing. If you have a column which is basically low impact, that means removing that column from your data set shouldn't really impact model results very much, okay? So in this case, if you're at the police x-ray website, okay, basically what it's saying for this particular outcome, the quarter of the year really had no influence, okay, on the predicted probability of this particular person's outcome with the police. So what that should mean then, if you remove the quarter column from your data set, your model's prediction shouldn't be influenced at all because it shouldn't have any impact. Okay, so that's what missingness is. Okay, and then finally here, okay, when it comes to consistency, it just means if you hold everything else constant and then you change one particular value, the influence of that particular value or column should go up or down in relation to it. Okay, so in this case, all right, if you compare the screen that I have right over here, okay, with the one that I had previously, okay, the inputs are all the same, okay? Someone got in an automobile accident, right? They're from the city of Charlotte. It's the second quarter of the year, Monday, okay? It's at noon right over here. Only difference though, okay, the value of age, okay, went from 40 to 50, okay? Okay, so meaning here, all right, we held everything else constant, okay? None of these other values are different, okay? We changed the value though, okay, from 40 to 50, okay? And then if you rerun the analysis, okay, the overall influence, okay, of the age value gets appropriately larger. Okay, so in this case, right, the contribution to the final prediction went from about a magnitude of 5% to a magnitude of 9%. Okay, now obviously how much something will change will depend, will depend exactly on the actual importance of the column itself, but that same basic property should be true. Okay. We're gonna go ahead, just so you know, I really like the questions in the chat. That's awesome. Okay. I'm gonna say that probably what we're gonna do is we're gonna have a few breaks throughout the presentation to kind of go over and answer everyone's questions. So I think Yannick's question is awesome. What does Shap use the data source? We're actually gonna talk about that explicitly here in a few minutes when we kind of get into the details. So that's coming up. And in general though, anyone who has any questions like that, feel free to put them in the Zoom chat. But we'll probably go ahead and then kind of circle around to them, and kind of answer them in one bulk, just to economize on time. Okay. All right. So in any event, All right, moving forward. All right, so in terms of some kind of explanatory model, all right, local accuracy, okay, missingness, okay, and then consistency, okay. A lot of these things I think are basically common sense, okay. I think they would probably seem fairly intuitive to us, but in terms of maybe in terms of like explicit criteria that a model would have to meet in order to be able to adequately explain something, these are kind of the three pillars that you should be able to go ahead and shoot for. Okay. So with that being said, this brings us to Shap, okay, which I actually think it's a somewhat twisted acronym. Okay, what it actually stands for is Shapley Additive Explanations. Okay. So in any event, this was a newer technique that was developed at the University of Washington fairly recently. I believe in 2017 was when they first broke ground with it. Their more polished implementation didn't really come around to about 2019. And it's definitely had a very, very big impact over the last 2 years or so, okay? So the idea here, it is a game theoretic way, okay, to explain the contributions of any particular model, okay, regardless of how it arrives at its answers, okay? When you're computing a Shap value, all right, there are really two fundamental kind of theorems or ideas that are kind of powering its results. Okay, one is game theory, which is actually, I think, not very intuitive. When I think of game theory, I think of maybe military generals, kind of talking about different types of strategy to take, or maybe executives in a boardroom, or maybe plants, in biology, how they might kind of, change their evolutionary adaptations to get more sunlight, things along those lines. I don't really think about machine learning models as really being an application of game theory, but it turns out that's not the case, okay? And so there's actually important game theory involved in computing Shap values. The second one is a more traditional machine learning concept, and that's permutation, okay? Permutation is a very common way of developing statistical inference for non-parametric models. It's basically built around the idea is that by deliberately changing the arrangement of certain items within a system, it's actually a way to measure something's impact. Or maybe in a more plain English, if you remove something and see what changes, it kind of tells you what the overall importance of that particular value or column is, okay? So what we're gonna do here, we're gonna go to a notebook here pretty soon to kind of walk through a Shap computation and sort of like with first steps. Let's kind of talk about some of the basic ideas, okay? In terms of how this actually applies to Shap. So Shap stands for something called Shapley Additive Explanation, okay? If you actually do some research, something called a Shapley value is a very, very kind of old-fashioned concept in game theory, okay, about how to distribute payouts to different players that are competing for some particular prize. Okay, that sounds kind of vague here, particularly right when it comes to something like ML or data science. Okay, but the way you would actually frame this, okay, in terms of a model, right, is that essentially, all right, the players in our game are the individual columns or features within our data set. Okay, here we're looking at kind of a tabular data set. Even if you had unstructured data like an image or text, the same basic idea would apply, okay? If you had an image, you could basically think of every single individual pixel or groups of pixels, right, as being a particular player, all right? And then essentially the prize, all right, that these players are competing for is the overall predicted value itself, all right? And then in terms of payouts, right, for competing for a prize, okay, the payout, okay, is basically the contribution that gets allocated to each individual feature for the model's predictions. Okay, so if we're at the police x-ray website and we kind of go ahead and run analysis, okay, that will basically tell you, right, the amount of payout that's being allocated to each individual column for that particular prediction. All right, this is kind of like the basic idea of game theory that's going inside the calculation, okay? And so this is really where Shapley comes from, okay? So it turns out there's kind of an important idea called a Shapley sampling value, which is really kind of the basis for Shap itself as a way to kind of contribute payouts in a very, very robust and consistent manner, regardless of what kind of situation that you're in, okay? So when you hear something about Shap, right, it's just kind of based off these game theoretic foundations, that's what it's referring to, okay? Now, how these payouts, okay, are actually computed, okay, for each of the individual features within your data set, all right, that's where permutation comes in, all right? So in this case, all right, what's happening very, very specifically, all right, imagine you have two samples in your data set, okay, sample 1, sample 2, all right, and you want to be able to calculate, okay, the influence, in this case, of let's say something inside the room column, right, which is 6.575, right? So how much is something like that, okay, contributing, to whatever your model's prediction is, all right? So the way permutation works, okay, in computing a Shapley value, all right, I call them Franken samples, okay, but you can call them something else if you want to. Essentially what you do is, all right, if you're trying to calculate, okay, Shapley sampling value, basically Shapley contributions for this particular sample, you would randomly sample, okay, something else from your data set, all right? And then what you would do then is you would make a hybrid combination between the two. Okay, so we look at this right over here, all right? The bottom 5 values are all drawn from sample 1, okay? The rest of the samples are drawn from sample 2, okay? So each of these samples are basically spliced together from the 2 previous ones. But if you're calculating, okay, the contribution, right, of the value of room, what you would do then here is you would deliberately, all right, in one sample, use the value of room from sample 1, and then in the other sample, okay, use the value from sample 2, okay? So this is kind of a random hodgepodge of 2 samples, but with one particular column deliberately held separate, all right? And then what you do then is you take the difference in predictions, all right, between sample 1 and sample 2, all right? That would give you some kind of number, all right? And so the idea is for that particular permutation, okay, that would be the marginal contribution, right, of changing the value of room, in this case from 6.42 to 6.57, all right? The idea though, all right, if you do this over and over and over again, okay, continually drawing random samples from your training set, okay, and then also, if you continually draw different random combination of columns from each of the 2 samples, and then you go ahead, take the differences and then average them out, that will give you the marginal contribution, okay, of that particular value inside your data set, okay, relative to all the other possibilities, okay? And so that calculation, okay, when done through all of your individual columns for all of your individual samples is what a Shapley sampling value is, okay? We're actually gonna go ahead and then see this, okay? Prevented. So keep in mind, okay, I'll go over a few things over here. So one thing over here about the sampling, okay, something about the slide itself. Okay, if you look over here, the differences between these 2 samples is actually quite subtle. All right, and so it is actually important detail, okay, to go ahead and then wrap your head around. So if you look at Franken sample 1 right over here, okay, and then if you look at sample 1 right over here, okay, the big thing here, okay, the columns crime through Knox, okay, basically belong to sample 1. However, though, if you look at the values for age right over here, okay, and you know what? I actually did make sample 2. There is actually a little bit of a mistake on my slide. I apologize here. Okay, so excuse me. You know what? Thank you for pointing this out. Important detail here. Essentially, what should have happened here? I'm sorry, I actually apologize for this. Okay, the top here should all be from sample 1, The bottom here should all be from sample 2. I actually made a mistake. This is a typo, so thank you for pointing it out. Okay, and then the two things that are deliberately held separate, okay, should be the values of room right over here. Okay, so I believe you pointed out was Ilya. So thank you. Yeah, there is an error on the slide. Okay, and so I appreciate that. So yeah, so down over here, right over here, these values should match. Okay, but I overlooked that when creating that. So thank you for pointing it out. So everyone here, let's make a kind of a mental note, right? These values should match from sample 1. And on the bottom over here, either 78.9, the 4.96, the 2, the 2.42, whatever. Okay, all of these should actually match over here. Okay, so you have a random mix between sample 1, sample 2. And then the things that are deliberately held different are the values of room. If we were to calculate the Shapley sampling value, okay, for the room column itself, okay. So again, we'll actually, I think we'll probably round up some of these answers to these questions as when we kind of finish up this next slide here, okay. We're gonna getting ready to a point where we're gonna go ahead and then answer a few things. What we're gonna do though here, everyone, if you wouldn't mind, okay, is let's go to this link right over here. It should be in the Slack channel. Okay, also if you go over here, I can go ahead, I think, Rose, if you want to go ahead and put it inside the Zoom chat as well. Okay, it should be further up in the Zoom chat. Okay, if you want to go ahead, we can click on this link. This is going to give us kind of like a kind of a sample calculation, okay, of a Shapley value, okay, and then we'll kind of talk about specifically how Shap takes this, and then and it kind of improves upon it, okay, in different ways, okay. But this is kind of like the core Shapley sampling value, which is kind of the game theoretic foundation of Shap itself. All right, so. The notebook itself should be called Shapley sampling values. You should be brought to something in Google Colab. Real quick, if you want to run this on your own, all right, you should be able to go ahead and go to File and then click on Save a Copy and Drive. Okay, and that'll take it somewhere where it's local. Okay, if you want to go ahead and then run this yourself, I would definitely recommend that. Okay, probably make it a bit more tactile. You can kind of see how these things work firsthand. All right, so what we're going to do here, you know, we're just going to take a look, right? Kind of like a sample Shapley computation. Okay, what it looks like. This is the unmodified version of it as well. Okay, you know, without any sort of additional optimizations. Okay, yeah, and so same thing, right? Real quick, it's worth pointing out here so that we just make sure we can run it ourselves. File, save a copy and drive, okay, and that should go ahead and then save you a local copy, and then you can go ahead and run that. All right, so what we're gonna do, one thing you might need to do here first also, no, actually, in fact, I don't even think you're gonna need Shap for this, so if you want to, you can probably just gonna go ahead and then comment this out, because this notebook actually doesn't even actually use any Shap. Okay, we're kind of doing it from scratch here. So we'll import NumPy, pandas, okay. We're gonna load in the Boston data set. And then again, Shapley is model agnostic. Yeah, and then go from there, okay? So you can basically, an important detail about Shapley's value is that it looks at differences in predictions by permuting different combinations of values. So it doesn't actually really care or pay attention to sort of what's happening inside the model itself, which is why it's model agnostic. Okay, in any event, okay. So we have NumPy, we have pandas, we're importing our data set. So same thing, this is very boilerplate stuff. We don't really care about the model so much right now. All right, so what we're doing here, okay, we're loading in X and Y. Okay, we're gonna go ahead and fit. Sure, so I think mentioned, let me know if this helps, if it's more legible. Okay, great. Okay, all right. So loading this in. Okay, again, we're not really going to talk about the modeling so much or how to get better performance out of a random forest or whatever. Okay, that's not really the purpose of this this workshop. All right, we're going to take a look at the head of X. Okay, it's the same thing. If we're not familiar, this is a very common data set, probably the most commonly used one, for looking at regression problems. So the idea is, this is a data set about 500 different houses that were sold in the greater Boston area. And so you have 13 columns, which basically describe, different characteristics of a housing neighborhood and what it's sold for. Okay, so if we're at all curious, there's just things like the crime rates and then the room and the age of the house and things like tax rates and that sort of stuff. Okay, so now the idea then, all right, with this particular data set, and then we have a model that's fit on it. Okay, what we're going to go ahead and do here is actually kind of walk through computing, okay, an actual Shapley sampling value. Okay, and this is kind of like the base computation that's used inside Shap, okay, with quite a few enhancements, okay, but this is kind of like the basic kernel that's going on, okay. So what we're going to do here, okay, we're saving a few variables. We are saving the columns in X, okay, and then we're also making a copy of that because the big part of what a Shapley sampling value is randomly shuffling the combination of columns that are being used inside the Franken samples, okay. Because an important idea of sort of how it kind of arrives at its value is that every single time you actually get two random Franken samples, they have different combination of columns in each one, okay, which kind of allows you to measure, the contribution of a particular value relative to different combinations of columns, which is something that's typically done to help combat, multicollinearity, which was mentioned in one of the questions, okay. Another question is like how many runs or how many permutations do you have to do? Okay, the answer is to get the exact value, you have to do a lot. Okay, in practice though, what you do is you do enough until you get some kind of convergence. All right, and basically where the additional improvements the additional improvements or additional change in the Shapley sampling value basically falls below some sort of threshold where making additional iterations doesn't really have any kind of improvement. Okay, and so basically in this case, to calculate a single Shap value, okay, we're going to go ahead, all right, and then go through 1,000 runs, all right, and then this is just the index that we're going to sample from X from. Okay, so let's run these variables. Let's run this notebook over here. Okay, so now the idea then, what we're going to do is we're going to go ahead and we're going to calculate, okay, Shapley sampling values for one particular sample, okay, just one, okay, which in this case is going to be the very, very first row of the data set, okay, and so that's what X is going to be right over here, okay. Then what we're going to do here, okay, we're going to randomly sample another value from X, okay, which is we're going to call J, all right. So X is basically going to stay the same throughout this exercise. J is going to continually be different, okay? So every single run, okay, J is going to represent a different value, all right? So if you just kind of want to inspect these things, okay, we can see the differences between X and J, okay, and what they're meant to do. Okay, and again, this is just for demonstration purposes. If you just kind of want to take a look at these things and see what they're doing, all right? This is kind of important detail, right? We talked about like permutation. So this is kind of where it's happening right over here. So what we're doing here, this is our list of columns, okay? And then we are randomly shuffling this, okay? And we do this, okay, every single time we do it, all right? Because an important part about Shapley sampling is, again, you have different combinations of columns coming from sample one and sample two. So what we're gonna do, we're gonna go ahead and randomly shuffle our columns, all right? And then we're going to reorder, right, samples J and sample X, okay, according to that new random order of columns. Okay. Now, these next lines right over here, okay, we're initializing two different variables, okay? According to kind of the literature, you should look at the official paper, right, for Shapley sampling. it would call this, xm plus j, xm minus j. So again, I'll sort of answer a bunch of questions while we actually in a few minutes here, we'll be at a decent spot. Okay, so kind of one thing I want to go ahead and bring our attention to here, okay, is we have xm plus j and then xm minus j right over here. Notice here what we're doing. Okay, we're saying, okay, starting at the room column, okay, set all the samples in this one equal to j, okay, but make the value for room itself equal to the value in x. Okay, and then over here in the next variable, we're basically doing the exact same thing, okay, but we are omitting rather this one particular step right over here. Okay, so the idea then, okay, these two samples right over here, xm plus j, xm minus j, okay, by basically saying make everything from room onwards, okay, equal to what's in j, but then sending the 1 and x right over here. All right, what we have is something that is functionally equivalent, okay, to our two Franken samples. Okay. And so what you'll see over here, right, again, there's a mistake in my slide because these two values should match right over here, okay? But so basically what we have now is we have two samples, right, where the top one right over here, right, all the values from sample 1, the bottom all from sample 2, but we've deliberately kind of changed the two values, right, in room over here, 6.575 and then 6.42 right over there. Okay, so the idea then, all right, these are our two values. All right, so again, if we want to inspect them, that we can, right? So they have shared combinations of the two individual samples, but the values for room are deliberately held separate, okay? So now the idea then, okay, this next step that we're gonna do over here is we're just gonna kind of go ahead, all right, and then this is kind of formatting it to make it ready for predictions. All right, so then what you do then, all right, is you look at the differences in predicted values, okay, for the two individual samples, okay? And so the idea is for these two particular samples, this is the marginal contribution of kind of going from changing the value of room from one thing to the other relative to all the additional columns, all right? So now the idea then, okay, this is just one particular sample, okay? So it's not like you just do this once and then you're done. The whole part about like Shapley sampling, okay, and permutation is that you kind of have to go through this process, okay, a number of times, and then you average out the differences, okay? So what this next line does over here, okay, basically we'll go ahead, take all these steps that we just did, okay, and then put them into a loop. All right, so if we go ahead and run this, all right. Now someone had a question, so sort of, how many runs do you have to do? Things like that. Okay, there's kind of a heuristic where typically anywhere from about 500 to 1,000 will typically be adequate. Okay, but also the way these things are implemented is they have, something kind of like a tolerance level. Where after they've done so many runs, and so basically no more improvement is being done above a certain threshold, then it'll go ahead and then turn itself off, okay? But you'll see here an important part about Shapley sampling, okay, is that it is an approximation technique, okay? It's based off of random sampling, which means you'll converge towards whatever the true marginal contribution is for that particular column value. But unless you run the whole thing into perpetuity, you won't get there entirely, okay? So the idea then, okay, once you're done, okay, you'll have all of your individual Shap values, and then you divide that, by the number of runs that you did. And that's basically the Monte Carlo approximation of the Shap value for that particular column for the sample. All right, so we run through this. Again, it probably is going to be a little bit different for different people. But again, as you sort of did more runs, this would eventually go ahead and then converge towards the same thing. Okay, so what we're going to do now, if you go to the next line, okay, this would basically kind of go ahead and do the same step, okay, except do it for every single individual column. Okay, and again, this is going to go ahead and take a while to run. All right, so let's go ahead, if we want to, let's run this. All right, this is going to take a while. Okay, so this will probably be a good time just to kind of go ahead and then walk through and then answer various types of questions. Okay. Okay. So I'm going to try and start from the top here. One question that we got is sort of, what's required, to compute the Shap value, things like that. Okay. So here, hopefully after doing this, all right, the answers may be a bit more clear. You actually need all of your training data. Yeah, and then, so you basically need your training data to derive the Shapley value, okay? Which is actually a little something of a drawback, okay, in practice, because it means it's a bit more computationally intense, okay? Because you kind of have to sort of, you fit your model, and then you kind of almost reuse the model pretty extensively to derive the Shapley value itself. All right, and then the good question here in from Zoom here, yeah. So Shapley basically works, yeah, on both. You need both the randomly generated samples from your training data, and you also, yeah, do need the model itself. Okay. All right, a few questions came up about like non-collinearity and things along those lines. Okay, generally speaking, okay, Shapley does assume non-collinearity. In practice, though, there are actually ways to calculate different types of interaction effects, okay, between different types of columns. One other thing, which typically is useful with Shapley as well, is every single run, all right, you have different combinations of columns. Okay, so in practice, when you're actually kind of calculating out the change, right, from going from one value to the other, you're actually comparing that to the particular values in certain types of columns. And so because the sets of columns that you're calculating the Shapley value against changes from every single time, typically does do a good job of separating out potential interaction effects and then getting something for that particular column itself. Yeah, but Shapley value all by itself basically does kind of assume you have this independent effect for every single column. Okay, one thing we're going to go ahead and talk about when we talk about Shap in particular is basically how you calculate interaction effects. And so it turns out what you can do is you can calculate Shapley values jointly with different combinations of columns and then subtract out the differences to kind of get the main effects and then contributing effects from individual columns. So there's a bit of an improvement on that with the actual Shap software library. But Shap by its Shapley sampling value by itself is going to assume independence between the columns. Okay, so let's take a look. A few more questions here. All right, so we have multicollinearity. We have the issue about sort of what you actually need to compute the sampling value. Another question that came up here. So what if Franken sampling creates totally illogical samples? Can this be prevented? The answer is, for the most part, not entirely, okay? But the whole point of sampling, though, is that you actually go through enough iterations that it kind of gives you basically, different sorts of contributions from a very, very wide variety of combinations within your data set. And then anything that you would do, right, from Shapley would actually just be drawn from your training data itself. So it is true, you probably would get some fairly, weird or erratic values occasionally, but the whole point of the Marty countersampling is to kind of average those things out, okay? Yeah, so actually another question here. So the Shap library can compute the Shapley values given a single example. So what we're actually doing right now is we're actually, the actual training loop that we just ran, okay, that might be in your Jupyter notebooks, is actually calculating the Shapley values for a single sample. Okay, so one thing that kind of jump out to you, Shapley sampling all by itself without any other improvements is actually fairly slow, okay, which is one of the reasons why it hasn't really taken off. Okay, let's take a look at some more questions, okay. One is that, so do 35% of police stops in North Carolina actually result in an arrest? The answer to that is no. For whatever it's worth, there were different types of weights that were reapplied to positive instances in the data set to make sure feature interactions were basically kind of discovered more carefully. In practice, the actual amount of police stops that actually result in arrest is closer to about 2 or 3%. Okay, but that particular application was built to sort of make sure interactions between different features was more vividly kind of like clarified. And so therefore the positive samples for arrests or stops were actually upsampled considerably, which is why the base prediction itself is actually a little bit different. All right, that's more about the actual application that we were using, not actually sampling itself. So Jessica has a question here. Okay, do you have 3 loops? Creating lots of Franken samples, holding your features constant, do this for each feature, loop over all second samples. If you actually look at the actual code snippet that's running, you take a look over here, okay, there are just 2 loops. Okay, so we're looping through each column, and then for each column, you know, we're generating the different samples. And then within right over here, we're creating a new random selection right over here. So you do get a new random choice, rather a new random combination of columns in each individual run. But I would say it's probably done inside the loop itself versus kind of as kind of its own individual loop right over here. But there are just 2 loops, but within one, we always generate the new random combination of columns. Yeah, so Shap itself, we're going to talk about what it does is it actually kind of takes the idea of Shapley sampling and then kind of co-ops it specifically for different types of ML models that are commonly used. Okay, and so for example here, like if you're doing a tree-based model, it would actually basically generate the Shapley values from the individual nodes inside the tree. So you wouldn't actually just need training, like the values specifically within the training itself. It could be calculated on the fly. Okay, yeah, and one-hot encoding, this came up a few different ways. One-hot encoding would also more or less be fine. Okay, where it would, you'd basically, yeah, just kind of go ahead and then just change something from 0 to 1 or 1 to 0, and then just test that against different combinations of columns. It turns out too, just so you know, randomly shuffling the columns means the number of potential permutations you could use for any sort of sample are actually quite large. Okay, they're pretty doggone big. Okay. So it turns out Shapley sampling on its own doesn't actually, its logarithmic time is actually pretty high. It's 2 to the power of k factorial. Yeah, so it turns out, we'll talk over here, Shap basically does kind of hold a similar combination of pixels constant at one time. Okay. And then likewise, also you can use it for various types of interaction values as well, to kind of calculate the joint effects between multiple columns at one time and not just one all by itself. Okay. In the interest of time, I'm going to go ahead, okay, and keep moving here. All right. So the idea is once you're done with this loop, okay, you'll have a big combination, right, of all these sampling values over here. Okay, and then the idea then, all right, if you average these out, okay, these would be the average values, okay, for this particular sample right over here. And so then the idea then, all right, if you look at this, okay, and then you add up, right, the average value, right, of each of these individual columns, okay, and then compare that to the base prediction right over here, you actually get something that in practice is quite close to your model's prediction. Okay, now again, this is a sampling technique, it's an approximation method. So the idea is we actually didn't cover like every single possible permutation of columns, okay, and then kind of calculate their marginal contribution. But you can see here, we converged towards something that is pretty close, okay. So basic idea here, what we just kind of discussed, let's kind of talk a little bit about, so kind of what this means, all right, in various contexts, okay. All right, so something that is useful, okay, about Shapley sampling, okay, again, it actually does meet kind of the criteria that we talked about before, okay. The only thing it really looks at, okay, are differences between, model predictions, for different types of Franken samples. So therefore, it doesn't really rely in any sort of, actually really any way at all, with respect to, what kind of model that you're using. Okay, so it is a model agnostic method. Okay, generally speaking too, all right, because you're constantly kind of like calculating something against different combinations of columns, it is pretty good at isolating the independent effect from that particular value. Okay, simply just by continually computing it against, sort of like different types of random shuffles, again, which will kind of indirectly capture different types of contributions from the different columns over time, okay? So it is usually pretty good at isolating the independent effects. However, though, there are a few things which are a little troubling about it, okay? To actually fully compute, okay, a Shapley sampling value, it's actually fairly time consuming, okay? So if you see here, what it does, the actual, algorithmic time of it is actually scales in 2 raised to the k factorial, okay? That number gets pretty big, okay? In this case, k is the number of columns in your data set, or the number of features you want to go ahead and then calculate against. Okay, so so to kind of fully calculate the exact Shapley value would be quite cumbersome. Okay, so therefore, raw Shapley sampling by itself, okay, isn't always going to scale especially well for all models. All right, and the other things kind of came back to a question that people had. All right, is actually requires kind of full access to your data. Okay, which itself, is kind of a problem. Okay, not every single model interpretation technique does this, but in the case of something with like Shapley values, you do kind of have to keep on resampling from your training data to capture the marginal effect in various ways. Okay, so in any event, okay, this kind of brings us to the actual Shap library. Shap is based off of the Shapley technique, which has actually been around for several decades. The actual Shapley sampling, was derived and elaborated, I think sometime like late 90s, early 2000s. Okay, but what Shap does, actually allows co-ops the idea of Shapley sampling, okay, with other particular techniques. Okay, to actually basically allow the calculation of Shapley values, but actually kind of co-opting other types of model interpretation methods. So that way you have faster and more exact ways of calculating Shapley values for wider varieties of model. Okay. Okay, so in this case, it turns out, if anyone's familiar with kind of like interpretable ML and things like that, there's things called, if someone mentioned in the chat, a LIME, tree interpreter, okay, and then something for neural networks called deep lift, okay. All of these are basically ways to kind of like understanding model output, okay. The Shap library basically takes these different ways of kind of basically traversing the model structure, different types of ML models, and then using those specific model structures to calculate Shapley values more quickly, okay? So whereas it probably took our CodeLab notebook, a couple minutes to kind of go and calculate the Shapley values for one sample, okay? Shap, as a library, allows you to basically calculate Shapley values more quickly across a wider variety of contexts, okay? And this is kind of its real technological breakthrough. All right. So again, this approach, it was written by primarily one person named Scott Lundberg, who came from University of Washington, okay? And so the idea then, Shap is basically a unified framework for basically calculating feature importance, okay, across a wide variety of models, okay? And so it allows you to do things like neural networks, or GBMs, okay, and actually have very specific and exact ways of calculating contributions of your input data, okay? And so that's really kind of the big breakthrough, is that sort of like regardless of the model that you have, you can basically have a Shap value with it that kind of allows you for individual samples to understand what contributes to that, okay? So with that being said, let's go over here to our next notebook, okay? So Shapley sampling is kind of like more of the pure technique, right? And how it works. Okay, let's take a look at the Shap library itself. All right, and again, this is pretty much a more performant way of doing what we just did by hand. Okay, that was the old school way. Okay, but this way, we can kind of calculate Shapley values in a way that is more specific towards various types of models. All right, so same thing. For this notebook, your probably CoLab does not come with Shap installed right out of the box. All right, so if you will, make sure you have this line pip install Shap right over here. Okay, so we'll go ahead and run it. And again, we should go ahead and get Shap installed. It takes a little bit of time. Okay. So again, I'll kind of talk about here. So, Shap is basically a more flexible and then faster implementation of calculating Shapley sampling values that are specific to different types of models. It's two different things wrapped up into one. All right. It is a computational tool. All right. It turns out you actually No. So yeah, you couldn't use it for unsupervised learning. You can use it for unstructured data. Okay, like you can kind of calculate the contributions of individual words or groups of pixels or things like that. But no, you wouldn't actually be able to use it for unsupervised learning. Okay. Okay. Shap is probably not as good a tool as other things for performing feature selection itself. Okay, rather, I don't know that it would actually contribute very much. That's something maybe just kind of like standard feature importance would or wouldn't. For whatever, I actually don't think it's its primary purpose. It's actually just better for whatever data that you have, for just kind of understanding interactions within it. You could kind of do it for that because you could actually look, something with a low absolute Shap value throughout an entire data set would be an unimportant feature. And so therefore you could use that as kind of a choice, to remove something from your data set. However, I don't think it would actually necessarily have a comparative advantage compared to other techniques for it. Okay, in any event, so we go ahead, we import this right over here, okay? It's the same thing. We're gonna kind of come up with kind of like our very simple model here, all right, with Boston. And then we'll go and do a random forest regressor, okay? So big thing, right? Shap comes with different built-in methods for specific types of models, okay? So basically, there's something called tree explainer, which allows you to go ahead and calculate Shap values in a way that is very, very particular for decision tree-based models, okay? If you're dealing with neural networks, okay, you have a deep explainer, okay, which is the same thing, which is a little bit more kind of closely attuned, to performing, feature attributions for deep models. If you just want a model agnostic way of calculating feature contributions, there's something called the kernel explainer, okay, which is about on par. I think Artem's comment here is probably what I would say too, where like you could probably get kind of similar results using Shap as something else, but I just don't know that it would perform any particular really comparative benefit, compared to other things that you have at your disposal. Okay. All right. So in any event, okay, what's useful here about Shap, right, is it kind of gives you a more faster, more exact way of calculating Shapley values across a wider variety of different models. All right, and so the idea then it looks like I actually sorry, you'll notice here I actually had a small typo here. Explainer right over here, okay, should be boss underscore explainer. Okay, so everyone wants to go ahead and note that. Okay, so all right, so my apologies. All right, so the idea then, okay, kind of the core contribution, right, of the Shap library, what it really does that's unique, okay, is it just gives you a very, very fast way to calculate the Shapley values for various types of models. So in this case, if we're looking at this right over here, okay, where we passed in x underscore boss right over here, okay, all right, is basically it went ahead and then calculated the Shapley values for everything inside of our training set. Okay, you might be noticed this actually happened much more quickly than what we did in kind of like our standard standalone sample. Someone mentions like if you have like test data, okay, or if you have out of sample data, things like that. The idea is you actually could go ahead and then still calculate Shapley values for them, right? Because it's actually very useful, right, to have out of sample calculation of feature contributions for new samples. The only thing you'd actually need to do that was a little bit different, okay, is actually when you initiate the explainer right over here, you could actually go ahead and then pass in your data set here at this step. Okay, and so then at this point, I would go ahead and then calculate the Shapley values there. And then if you pass in the new sample right over here, like an individual sample from your test set or something new that was coming in live, okay, it could basically then go ahead and then calculate the Shapley contributions based off the training set that you had in here. All right, so important point, yeah, you actually can use Shap to kind of calculate, Shap values for individual samples that are out of sample. Okay, but in any event, okay, really one of the big contributions, okay, and not the contribution, right, is the ability to calculate Shapley values kind of across a wide variety of different models and contexts. Okay, and so same thing here. You have a base value right over here, 22.54. Okay, and so then the idea then, right, if for each individual sample, if you add up the Shap values, okay, and then add them to the base value, that'll go ahead and then give you your model prediction. Okay, so this really is kind of like the fundamental sort of progression or technology inside the Shap library is being able to calculate these values very, very quickly. Something else, though, it typically does quite well, all right, and on top of that, is it gives you a number of different graphing tools for being able to visualize them. Okay, this is just kind of standard matplotlib. So for quite a few of these charts, you could probably just recreate them on your own if you wanted to. Okay, but we'll go ahead here. All right, and just kind of take a look at some of the base functionality, okay, inside the actual library itself. Okay, this is just the actual average absolute value, excuse me, of Shap values of each of the individual columns. This corresponds reasonably well to something like feature importance that you might be used to doing. They'll typically give you pretty similar results. Okay. But again, something about Shap, which is very, very nice, right, is you actually have these sort of like feature contributions, both at a global level right over here, but you also have them for all of your individual samples. Okay. So in this particular case, all right, what you're able to do here, and again, if you wanted to, you can kind of like take your Shap values and like put them into your own graphing solutions if you wanted to. This is kind of a nice way of doing it. This is a bit more handy, is you can actually see the distribution of your Shap values for each of the individual columns. All right, this is kind of something where, you know, it kind of does what things like feature importance, or maybe to a lesser extent, something like partial dependence can't do nearly as well. Okay, so in addition to kind of like global averages, you can see how something like, you know, feature contributions are distributed, okay, across throughout your entire data set. Okay, and you kind of see like some of these tend to be bunched together, others tend to be a bit more spread out. You know, sometimes it can be interesting. You know, you might have like a male, female, you know, column or individual groups. Okay, so if you kind of want to isolate the individual impact, you know, of discrete categories, things like that, lots of times this kind of allows you to kind of see visually how different types of model contributions are bunched together across features. Okay, and then we'll go through a few more of the charts here. This right over here is literally just kind of calculating like Shap values across different values of a particular column. Okay, which you can see over here like this. All right, and then also here, Shap typically has very, very useful facilities for visualizing model contributions at the level of a single prediction. Which is often some of its most, I think, most important benefits. So the idea then is if you have, you know, an individual prediction that's out of sample, something new that's coming in, okay, and you're using something like a GBM or a neural net or things like that, and you want to understand the kind of like what's actually contributing to this predicted value, you can go ahead and do that, okay? Pretty much the two standard ways of doing this, okay, is something called the force plot. Okay, and then it also has kind of a zippy waterfall chart as well. Okay, same thing, where you start with the base contribution and then you go ahead and then add up the individual contributions from each individual column and things along those lines. Okay, and again, all of these charts are basically just drawn from the actual basic Shap value calculations. Okay, but you know, this is visually, I think, pretty easy and kind of gives you pretty good out-of-the-box results. Okay, same thing. We're going to answer a few more questions towards the end of class here, which is actually coming up pretty soon. So we'll kind of take note of what's on people's minds and then go from there. What I'd like for us to do now here, okay, all right, is at least for a little bit, okay, let's take about 10 minutes or so, all right, just so there's a little bit of hands-on exercise, because I know here it can be a long time to listen to one person talk for a while. Over here, down here in the notebook, okay, this is a small exercise. So what we did here, we loaded in a new data set, all right, and so essentially what this kind of comes down to, all right, is just being able to recreate some of the charts that we had above over here, but for a separate data set. All right. And so the starter code is right over here, right? You have X and Y, and then you go ahead and fit your model. So assuming you have it saved in Drive, okay, I'll say let's take about 5 to 10 minutes, all right, and just try recreating a few of the different charts. You're given a prompt of some different questions right over here. You know, the 3 most important features, okay, or how does it interact, kind of like how does it change across the data set, okay, and so on and so forth. Basically, all of these things, okay, could be answered by pretty much recreating different versions of these charts right over here. So this is a simple exercise But lots of times doing things on our own, I know, can be a bit more interesting and engaging than just kind of listening to me here for the full time here. So let's take about 7 to 8 minutes, everyone, okay? And just kind of go ahead and just kind of work through these as much or as little as you like. And then at about 40 past the hour, we'll kind of come back here and then just talk about a few more remaining details and then go from there. Beautiful. Okay. All right. So again, hopefully that's an example, maybe just to kind of take a look, right? Kick the tires a little bit. I know, it's not a huge amount of time, but it's something to kind of reproduce some of our own output. So we have longer questions that I think are probably worth answering in different ways, which are really, really helpful. So what I want to do here is I just want to go over a few of the remaining points regarding Shap and how it can be used. And then we'll see if we can maybe take out the last 10 or so minutes to kind of go over everything. So real quickly here, for all of the examples that I'm going to be doing, you can go ahead and then run the corresponding code snippets over here, okay, to go ahead and follow along. So for example here, the first thing we're going to talk about now are interaction values. Okay, that Shap can go ahead and then calculate for you. Again, this is a big thing, right? Because we had a few questions like multicollinearity. Of course, too, if you're using tree-based models, tree-based models have the benefit of actually capturing pretty elaborate sets of combinations between different sorts of features, things along those lines. All right. So the basic idea here, okay. In addition to kind of calculating, the separate Shap values, right, for each individual column. You can also calculate a Shap value that actually takes the overall Shap value for a particular sample, okay, and then actually deconstructs it into the independent effect to that column, and then the contributing effect from every single subsequent column inside your data set. All right, and so basically the way that would work, okay, it's computationally pretty intensive. It can take a little bit of time to go ahead and run. All right, but the basic idea here is, in addition to being able to kind of calculate the Shap value, the Shapley sampling value for a particular column, right, by holding one constant instead of setting the other one, looking at the other one between the two samples, you can also then, essentially what you do then is you do that for two columns jointly, okay? And then what you do then is you take the main effect and then you subtract out the contribution from that individual column to kind of get the contributing factor for each individual feature within your data set. So the idea is you can actually take the idea of a Shapley sampling value and have kind of like the unexplained Shapley effect that's just kind of for that particular column, and then all the individual contributions from everything else inside your data set. So if you're looking for kind of like how things might coincide with one another or concurrence or things like that, you actually have those capacities. Okay, and so the idea then, what you get as a result here is multi-dimensional, so it can be a little bit difficult to wrap your head around. So when you actually are done calculating your interaction values, this data set is 506 by 13. Okay, when you're done here, you're actually going to have a 506 by 13 by 13 data set. Okay, so meaning when it comes to interaction values, okay, each row, each sample is going to have its own 13 by 13 matrix of interaction values, okay? And then if you wanted to, you can go ahead and then see that over here, okay? I have some slides here which I think break it down, I think hopefully a bit more clearly. All right. So the basic idea, right, when you're done going ahead with Shap, you might have something for a column. In this case, we're saying it's 6.4, right? But again, the big thing is, different types of columns kind of contribute, right, to kind of the importance of a particular feature. So again, calculating the interaction, right, is again, kind of calculating the Shap value jointly with each of the individual columns, subtracting that out from the overall Shap values. That way you kind of have the main effect and then the effect you can attribute, to each of the, individual columns coinciding with it. So then the idea then, what you can do then is for every single Shap value, for every single sample, you have the main value, which is actually just the contribution of the main effect added together with all the individual effects from each of the individual columns itself. okay? And so effectively then, all right, when you actually have an interaction value, all right, if you actually look, okay, at the matrix, which in our case is 506 by 13 by 13, this is a simplified example, okay, if you had a 3-column data set, okay, and you're calculating the Shap interaction values for them, okay, the interaction values for a single sample would look like this. It'd be a 3 by 3 matrix, okay. The values going down the diagonal, okay, would sort of be the independent effects, okay, for that particular column, okay. Across each row, all right, these are the contributions for every other column inside the data set. And then if you add these up together, that gives you the final Shap value for each column itself. Okay, so you can deconstruct Shap values into various types of contributions from different combinations of columns, which lots of times is fairly helpful. So an example output is something like this. Nope, I think our slide's over here. Okay. So we looked at the Boston data set, right? This, if you'd actually model the interaction, okay, between LSTAT and then the room columns, okay, the idea is basically what this tells you, okay, is that lower values of LSTAT actually remove the impact of room. Okay, so that means as room gets larger, okay, its contribution gets reduced by lower values of LSTAT, okay, which you can see over here. But on the right side over here, right, if you were to generate a Shap chart for room and tax, okay, the fact over here that the contribution of room is basically unchanged by tax means that the impact of tax and then the impact of room on your data set are basically independent of one another. Okay, looks like we have a few questions about this. Okay. All right, so the idea then, so again, once you're done, you do have a pretty robust way of kind of looking at different types of interactions and how one feature might influence another and so on and so forth. Okay, real quick, and again, I would say if you want to run through this, we actually have, you can run through the notebook. If you're doing Shap for classification, the basic code works about the same way. Okay, the only difference, all right, the output that you're going to get is log probability, okay, which means when you're getting the feature contributions right over here, all right, if you exponentiate these, okay, it'll actually turn out output into raw probability itself, okay. In the actual demo notebook, you have some code snippets that show you both, one way or the other, okay. So I personally find it more intuitive, more appealing, right, to sort of say like the base prediction is 23% and this one added 4, this one subtracted 7 and things like that, so on and so forth. Okay, and again, the example there is in the Shap demo if you want to take a look at it. All right, but this is kind of like the base output for classification. Another big thing here, right, Shap also kind of comes in with guardrails built in for handling neural networks as well, okay? So there's a pre-existing algorithm called deep lift, which is typically used to kind of calculate relative importance to things like words or pixels or things like that to a deep learning model. Again, so Shap basically co-opted that and then used it to calculate Shapley values for it. And so the basic idea then, okay, I'll be honest, this part is a little bit buggy. It doesn't always work seamlessly. It depends a lot on what types of versions of the libraries that you're using, okay? But if you have something like a natural language model, you can actually decompose the contribution of individual words for a particular sample to see what they actually use to kind of go and contribute to the final model output. And then you can also do something for images where you can basically clump together groups of pixels together to figure out how they might contribute to a final predicted outcome for one thing or the other, okay? I would like to say this part right over here is completely seamless, but in my experience, you typically do have a little bit of friction getting it to work, but you do kind of have like a built-in native support for different types of neural networks. All right, so a few closing thoughts here. I think we're kind of getting close to our time. We have 10 minutes left. We want to obviously keep things open for questions. I know we have a few here, so let me go ahead. So just a few more points here I want to go ahead and bring up. All right, so interactions. Okay, so a few points I'd kind of like to point out here. Definitely, I know, like, if you look at different presentations here in PyData, you know, like causal inference is definitely mentioned quite a bit. I think this is worth pointing out. Shap, right, allows you to perform pretty elaborate model inference. So what types of patterns, right, were found in your data and how are they attributed, right, to different sorts of features, things along those lines. It's not quite causal inference, all right? With causal inference, you have to have some kind of counterfactual, right? Some kind of what if scenario, something else would have happened. And so if you have persistent correlations inside your data, like all throughout your training data, and something in your test set is genuinely different, right? It'll tell you basically based off what happened in your training data, but it's not quite the same thing. It's just kind of running like an actual controlled experiment or things along those lines. A lot of times these two are going to dovetail together pretty closely. But again, I think it's usually a good idea to distinguish between the two. Model inference and causal inference. Lots of times they will be pretty similar, but in my opinion, they're not exactly the same thing. Okay. Other thing too is it's important to think of Shap as basically being two things. Its core technology, right, is its ability to kind of calculate Shapley values quickly and efficiently. Okay, and that's when you go ahead and load in the model explainer. It also kind of has graphing utilities built on top of it. Okay. However, though, the graphing stuff that it does is actually just different types of matplotlib charts tacked on top of the actual Shap values that were computed. So you wouldn't necessarily have to do this. And so I've actually found on my own lots of times, if something like this is being used in applications or in dashboards or things like that, I typically just kind of take the Shap values and then pass them into like another graphing library or things along those lines. So they're not exactly one and the same. And then something else I'm going to point out, if you look through the actual Shap demo notebook, there are definitely a few extra lines added to kind of point out where something was a hack. So there is a little bit of headwind because sometimes you might have to do things slightly differently depending on what model that you're using. Okay, like I've noticed Shap for something like gradient boosting and something for scikit-learn doesn't always happen quite the same way. And then also Shap, as of now, doesn't actually support PyTorch for neural networks, only TensorFlow. If you actually download like a working version and then clone the GitHub repository and then use one of their working branches, I believe they actually do have some versions of it to support it now, but in terms of the official release, it's not there yet. Okay, but in any event, definitely it seems to be a very, very useful tool. Definitely in the last 2 years, it's become extremely popular. I actually believe it's one of the most trafficked GitHub repositories now in open source and ML. And so that's happened in a pretty very fast time. Simply because you know, it's the hole that it fills is a pretty important one, and it gives you a pretty good toolbox for doing lots of things. So hopefully you guys will have some additional you know, motivation and wherewithal to go ahead and do it, and a little bit of practice using it and some background information. That is all I have for today, everyone. Here's a link to some additional just helpful resources. I will post them in the Slack channel afterwards. Pretty much everything was more or less kind of covered in various ways throughout, you know, throughout the actual exercise itself, but just in terms of the actual repo or some of the literature that was used to derive it, things along those lines, it's all there. Okay, so let's go through a few questions here. One that stuck out, okay, a few people have. Okay, is, you know, how can a column have large and small Shap values at the same time? That's not contradictory whatsoever. Remember, so Shap values are for specific values and specific samples. Okay, and so the idea is, right, is for every single sample, what was the contribution for that particular value to a final prediction? Maybe kind of a useful analogy here is if you had something like income and then you're modeling that to kind of determine life expectancy, you'd expect, you know, someone with zero income, that number, right, would negatively contribute, right, to the final model prediction. Okay, but if someone, you know, is you know, in the top 1% or the top 1%, you know, you would expect that number to positively contribute, okay, you know, to the actual final predicted value itself. So assuming you have something on a numeric scale, there's no reason, smaller values, might subtract from a predicted value and larger values might add to a predicted value or vice versa. Okay.
Hello, Jonathan, just a reminder, I know you are controlling the watch, okay? So it's 5 minutes now, 4 minutes left, okay?
Okay, beautiful. Yep, no, I got it. Okay, yeah. So another question that we had here is, so something like a scatter matrix for interaction plots out of the box. Yeah, so I actually believe if you actually look at the actual Shap demo notebook, you actually do have exactly that, like a scatter matrix for interactions. So for anyone who's used to maybe using things like partial dependence, you can basically use Shap interaction values to accomplish something fairly similar. And so literally it's called the interaction plot. It's inside the notebook itself, but also again, probably following up, I can post a link to it from the GitHub repo. And then also, yeah, Shap does have built-in capabilities to basically look specifically for transformer models itself. So if you're using transformers for NLP, there's actually an aspect of the deep lift algorithm which has been built in the Shap that go ahead and handle that. Same thing, probably in the Slack channel, I can go ahead and then post up some follow-ups for that. But it's there. Okay. And then I think we've kind of covered everything, most of the things here, right? Yeah, so something I mentioned before, so with like something like a categorical variable, if it was binary, same thing, you would basically do 0, 1, and then just kind of contrast that with all the different kind of combinations, the columns and the permutations, and then you'd have Shap values. It's actually fairly common. If you have a column, yes, no, this binary, you typically will see the distribution of Shap values kind of cluster between the 0 and 1 values. In terms of time series, I actually don't think it has great coverage for true time series models. Okay. Obviously, if you had like time series data, like time series features, you could sort of look at the impact of that. But in terms of maybe looking at something like an LSTM on like a time series model or things like that, like a forecasting the individual steps, I don't think it would actually give you great coverage for that. All right. Okay, Jonathan, I think that's going to take me here pretty much. I think we're about time to head out here.
I'm not sure if you answered already this question, but I think it was Larissa was asking something about imbalanced data sets. So she was assuming that before applying Shap, probably you need to correct the imbalance in the data set, right? So she was asking for confirmation.
Yeah, if you're talking about something like scaling or standardization or things like that, really that shouldn't be necessary. But if you're talking about like literally something that's just, like a sort of unduly influences it, like in a way that's fairly noisy, yeah, you probably would want to remove it.
I think it's in the way that you have a majority class and a minority class when you want to classify something. For instance, like a suspicious spam filter or whatever, you will always have a majority class with a lot of samples and very few samples of the bad guys. So that's why when you have this imbalance, do you need to correct that before applying Shap?
No, in that particular case, no, you wouldn't really. That wouldn't really be an issue. The idea is if you just sampled it enough, you'd eventually get. You'd basically you could eventually sort of like you actually look at Shap values for each of the individual classes. Is basically the way it would work. And so therefore, if like not just for like a single like binary example, but for each individual one, you take them and then sort of permute the different values. So even if you had something that did not happen very, like it's only 1% or 0.5% of the time, things like that, it would actually go into look specifically for that particular outcome, hold that constant, and then go through the different permutations. So therefore you get the interaction effects. So there shouldn't be any sort of additional special treatment you have to do on top of it. Outside of like what you might just use to kind of get like the best model that you could.
Perfect. Okay, thank you very much. So this session has finished. And thanks to all the participants, and also a special thanks to our speaker, Jonathan, for the great workshop and for being here and part of the PyData Global 2021.